Hi everyone, welcome to iCANX Talks. My name is Lan Fu and I'm a professor in physics from the Australian National University. Today is the 184 iCANX Talks, and it's a great pleasure we have Professor Baohua from Royal Melbourne Institute of Technology, Australia, joining us tonight. And this is our panel tonight, which I'll be introducing them later this evening. So let me first introduce Professor Jia. Professor Baohua Jia is a distinguished professor and a fellow of Australian Academy of Technological Science and Technologies from Australia. And she's a future fellow of Australian Research Council and founding director of Center for Atomaterials and Nanomanufacturing at RMIT University. Before joining MIT in 2022, Baohua was a tenured professor at Swinburne University of Technology and founding director of Center for Translational Atomaterials. Professor Jia is a fellow of Optica and also fellow of the Institute of Materials, and Mining. Since 2019, Professor Jia has served as a College of Expert for the Australian Research Council. Her research focus is on the design and optical characterization of novel nanostructures and nanomaterials, fabrication, and efficient conversion and storage of light energy. Professor Jia has published more than 300 journal papers with an H-index of 72, and she has developed more than 20 invention patents and patent applications. Due to her outstanding contribution in scientific research, she has won many awards, including the 2017 finalist of Australia Prime Minister Science Award and many, many other awards, which I don't have time to talk about today. So without further ado, please join me to welcome Baohua to the stage. Baohua, stage yours.
Thank you so much, Len, for the very nice introduction. So let me share my slides. So can you see my slides okay?
Yep, so good.
Good. First of all, allow me to thank iCANX for providing me this wonderful opportunity to talk to the audience. And also thank you very much, Lan, and also the panel for actually to be here. Today is my great pleasure to talk about Atomaterials for sustainability. So before my talk, I would like to acknowledge my group, very hardworking group. All the work I show today is actually their really hard work and also their research outcomes. I'd also like to thank my funding body and also collaborators. So before the formal content, I would like to share with you, recently we have been funded a new center called ARC Center of Excellence in Optical Combs for Breakthrough Science. So actually in the past 20 years, I have been working on this integrated photonics using nanofabrication. And this optical comb is actually working on integrating the very large kind of optical devices to try to miniaturize this device and then integrate that into optical chip. So sorry, for example, this like several meter high device into this kind of finger top, this kind of device. So in this device, there are all sorts of optical elements, so including source and also the detector. So the key idea of our center is actually to try to use this kind of light source to be able to do all sorts of applications. So this including, for example, using microcombs for sensing the weather change, like our environment, and also to try to kind of forecast the environmental change. Because optical combs that can give you very precise frequency, and then any very subtle change in the environment can be reflected or measured by these optical combs. So in the meantime, the microcombs can be also used for astronomy to really understand the universe and also to find human-like kind of this kind of creature in the universe. In the meantime, we can also use the microcomb to understand the origin of the universe. So just talking about like understanding of human beings, so we actually quite far away from really understand the entire picture. So in this case, microcombs can also help us to really understand where the disease is originated. So this can start from the human embryo. This can also can help us to kind of predict or detect or even cure disease from the very early stage. So basically, this microcomb is very powerful. And then within the next 7 years, all our team is going to work together. So our team is from 8 different universities in Australia. And then we're going to focus on developing these optical combs and make that available, not only in the research labs, but also made that available for industry. So if you are interested in knowing more about the optical combs, our webpage is available now. And then we are very active recruiting PhD and postdoc. So now talking about the why we would like to work on these chips. So as you know, today I'm going to talk about this Atomaterials and also for sustainability. So if you understand that the chip, when we talk about the size, is actually there is a law called Moore's law governing the why we want to miniaturize our device, because the smaller the size of the chip, the faster speed, and also the like greener it is, the less energy it's going to consume. For example, nowadays we have 3 nanometer chip, and then you see that according to Moore's law, all this chip performance is actually going higher and higher. But actually, for the silicon chip, there is a limit. When it comes down to like 1 nanometer, the silicon chip is really reaching the fundamental limit. So in this case, so if you probably hear about Atomaterials, but Atomaterials is actually represented by graphene. That means atomic scale material. Graphene was discovered in 2004, and then only 6 years later, it won the Nobel Prize. This is because graphene got so many wonderful properties simultaneously. So this not only including electronic, magnetic, optical, it also means like thermal and also mechanical properties. So all these great properties make graphene a very outstanding material. So graphene is basically the first time separation of like atomic scale material from bulk. So because of all these very unique and outstanding properties, graphene helped these 2 UK gentlemen won the Nobel Prize within 6 years. So this is quite unusual because normally we are expecting that like the research finding can actually see the impact, then people will get an award of the Nobel Prize. So actually graphene helps to achieve much better performance and then using less energy consumption. And the discovery of graphene actually brings us to the point why within 6 years, actually graphene can help to get this Nobel Prize. So if we look into the human development history, you will understand that material development is actually the driving force of our human society. So if we look into like back into the very early stage, talking about each age is actually governed by one material. So for example, the Stone Age, Bronze Age, Iron Age. So each age is centered by one signature material. And currently we are in the information age, and then silicon is our signature material. But as I mentioned to you just now, silicon is actually approaching to the limit. What's going to be the next material? That's where Atomaterials start to emerge. And then this Atomaterial is represented by graphene. And the discovery of graphene actually triggered a family of two-dimensional material. So that means at the atomic scale, the material can be separated and made use of. And then in our center, we actually focus on this atom material. We want to look into the atom material, not only from the laboratory research point of view, but also bring that out of the lab and then make that into useful device and also some material that useful for our life. So we believe that this atom material is going to be like potentially the next next generation of this signature material. And then we believe that we should really do something to try to really research that and then bring that the benefit to the human society. So talking about graphene or 2D materials or atom material, you probably appreciate that since it is on the atomic scale, it's very thin. It's very difficult to handle. Originally, it was separated by using this Scotch tape and put on top of this graphite. After many times of peeling off, you will end up with this kind of flakes. And these flakes, they could be single layer or could be multi-layer. So it's really by luck. And then later on, this very sophisticated machine was developed using chemical vapor deposition. You can get large scale graphene layer or some other two-dimensional materials. But it's still quite challenging to get large scale, and also it requires lots of expertise. So really how to make monolayer graphene or monolayer 2D materials with controlled layer number or with large scale is really very challenging. In particular, in lots of devices, you will need this multi-layer stacking to achieve some very nice performance. However, using CVD method is very difficult to make. So in our laboratory, we develop a completely different route. So basically, we start from graphene oxide. The reason is graphene oxide is water soluble. It's basically have this graphene basal layer decorated with all this oxygen containing group. That makes the graphene oxide is very easy to process. It's wet chemistry can synthesis. And then by using laser pulses or some other method to provide the energy, all this oxygen containing group can be chopped off, and eventually you can convert graphene oxide into reduced graphene oxide, which has a property very similar to pristine graphene. So we, because we focus on optoelectronics properties, we measure the, for example, this optical property, which is refractive index and also extinction coefficient. So as you can see, graphene oxide actually has really nice, quite high refractive index, and also in the large range, the extinction coefficient, which means loss or absorption, is quite reasonable. It's very, very low. So in this case, we are thinking we can actually make use of this graphene oxide to make some large scale films. So in that case, we want to control the monolayer. Because in optoelectronic devices, monolayer is really important. It's also very easy to integrate with existing devices. So in this case, we develop a method called self-assembly method or layer by layer deposition. So basically, we have substrate and then put that into positively charged polymer layer, and then we put that into graphene oxide layer. After repeating, you can actually have monolayer of graphene oxide separated with this polymer layer. In that case, you can repeat this process to get as many layers as you want. So this method can control the layer number quite nicely. So in this case, you see that 5 layers, and then each layer, the layer thickness is very well controlled. And the advantage of this coating method is it can go really large scale and also with different substrate, which is impossible to achieve using CVD method. So in our case, we also tried how large we can go. Actually, this is decided by your like container. So in this case, we made an A4 kind of paper size. But as long as your container is large enough and then you have enough solution, you're able to coat that into large scale. So in terms of the coating quality is also quite consistent and also quite high. You can see that with layer number increase, the color is increasing, so increasingly dark. This is because of the absorption is increasing. And then within full size, full wafer size, you can see that the roughness is less than 5 nanometer. So one of the key advantage of this coating method is actually it can coat nanostructures. So for example, this is a photonic crystal structure, and then using normal coating method like graphene is basically putting just on top of the structure. But using our coating method, you can actually achieve this kind of we call conformal coating. So the coating can very nicely cover the entire structure without having the gap. This is quite critical when you talk about optical devices, because optical devices, you want that very nice coupling between the waveguide, for example, with the atomaterial. And then in this case, you don't want to see any gap. So this is basically the coating method. You can go large scale, different substrate. You can also cover nanostructure and then enable the functionality into different devices. So now with this coating method, if we look into the history of these 2D materials, you will see that actually these 2D materials or graphene oxide were synthesized quite a long time ago. Well, even after so many years, the coating method was not really having a huge breakthrough in terms of scalability and also the layer number control. And only until recently we could do this. And then that means we are able to really focus on different devices, whether we can enable this device into different existing architecture. So when we talk about device, you probably noticed that there is always patterning associated with the device. And then in this case, most of the existing method is using the like E-beam or focus ion beam fabrication. But in our case, we use laser. The reason we use laser is laser enables 3-dimensional structure, and then you can have high resolution, and also you can fabricate on existing device. So this is basically a fabrication process showing how we can fabricate Venus. So in this case, after the fabrication, you can see that this contour will lead to Venus on top of human hair. The fabrication can be very precise. It can the highest resolution achieved if you use 2-beam can reach 9 nanometer, and then most importantly, it can fabricate different materials. So we have been working on this like fabrication in the past 20 years, and then recently this one has been also commercialized. The machine is available. So using this fabrication method, we can chop off all this oxygen containing group and convert graphene oxide into graphene. And then that means we are able to have quite good quality, and then using simple and low-cost method. So during the laser reduction, you will see that the color, if you use different laser power, the color of the graphene oxide is increasingly dark. That means you're closer to graphene. So during this process, the two optical constant is actually continuously changed. For example, the refractive index is changed from 1.6 to 2.7. So this is a huge change. Remember, this is for a very thin layer of graphene oxide. And then this change is about 2 orders of magnitude higher than the normal bulk material. So in the meantime, the extinction coefficient is also changing very dramatically. So the change of this parameter means we're able to make lots of devices based on the contrast we introduced by using laser. So when we measure the band gap, you will see that after laser reduction, the band gap of the material of graphene actually graphene oxide changed from 2.2 to about 0. That's almost fully reduced and then convert into graphene. And we need to ask the question, by using this low cost and simple method, whether we have good quality of the film. So we actually measure that and compare with the CVD-made graphene. We found that it's actually quite close in terms of the surface conductivity. That means the optical property is really close. So during this process, as I mentioned, when we increase the laser power, basically graphene oxide is continuously tuned, and then this oxygen-containing group is reduced gradually and then eventually fully reduced. You will see the optical constant refractive index from low to high, the absorption from low to high, and also electronic property is also from dielectric into conductive. So that means we are able to make use of this property change and introduce some functionalities and also make some device. So now I will show what kind of device we can make. So in the early stage, when we see the large refractive index change and also the extinction coefficient increase, we were very excited. And then because, in the optical or integrated photonics, this area, making flat lens is really popular. It's actually like a long existing dream. Because, most of the lenses is actually very fat because that's based on the refraction. You need to have that fat lens in order to refract the light into a focus. But in this case, when we have the graphene oxide, we can just draw some concentric ring. This is very similar to like phenol lens, but you won't be able to achieve this very nice focusing with a phenol lens. Well, as you can see here, using this lens, we're able to focus the light into 3-dimensional focus. And also this one is diffraction limited. That means the resolution is really high. This is because of the benefit of having the large refractive index change and also the extinction coefficient increase. So in the meantime, we can also, because the film is very thin, we can fabricate that onto flexible substrate. Normally, for optical zoom, in order to achieve optical zoom, we need to have multiple lens, like a lens kit. And then the relevant movement of the lens to introduce the change of the focus spot. But in this case, we can actually change the vertical zoom, vertical movement into horizontal movement. And then by stretching the lens, we're able to move the focal spot. So this is basically achieve like flexible zoom lens, and also the operation wavelength is very broad because graphene doesn't really have dispersion. It's dispersionless. So in this case, we achieved the entire visible focusing or imaging. You see that the resolution of the imaging is actually quite nice. So this actually kind of initiate the research, because we can achieve the refractive index change. That means the phase change. And then in the meantime, extinction coefficient change, that means the amplitude change. So if you are able to control these two parameters together, you are able to fully control the wavefront design. So in this case, we can kind of encode like the different wavefront we want to achieve. So for example, in this case, we achieved this kind of multifocal lens. This is quite important for example, for laser trapping, for super resolution imaging. You can also encode like this like spiral phase and combine that with the focusing phase. So in that case, you have quite complex phase. But the fabrication is also just in one go. Basically, one fabrication can give you multiple phase. And then this way, you can achieve this kind of OAM beam, which is very useful for example, for quantum optics and also for laser trapping. By the way, so this one, if you want to achieve using conventional way, you have to use SLM and also multiple optical element, very expensive one. But this one is only like one film, very, very thin film. You can achieve different topological charges and also like different order of the focus. So in the meantime, we can, because of the graphene oxide lens is so tiny, we can integrate that into the fiber tip. And then in this case, to achieve quite nice focusing. And this one can be used for endoscope and also for fiber lens for telecommunication. Yeah, this one is in collaboration with Professor Lin Ma. And then we also would like to see, because this method, we are working on really, really thin layer of materials. So previously it's all on the like 100 nanometer scale. But then we want to explore, so what's the thinnest lens or thinnest optical device we can fabricate? So in this case, we use this monolayer TMDC lens, and then it's only 0.67 nanometer. We use the laser to fabricate this concentric ring structure, and then we found that the focusing is actually really, really good. And using such monolayer lens, we're able to achieve the imaging of some characters, first order and second order imaging with high resolution. So this is the thinnest lens, because it's monolayer. You cannot really go beyond monolayer. So in the meantime, there are also other optical elements you can fabricate. So for example, the IR polarizer, because graphene oxide has really nice IR property, very low absorption and high refractive index. So using the simple grating structure, you're able to make an IR polarizer. So otherwise, polarizer is very difficult and very expensive to make. So in this case, you can achieve quite high extinction coefficient, extinction ratio in this case. And then the film is only about 2 micrometer. So other device like display, because the film thickness you can control, therefore you can control the interference condition by changing the film thickness using laser exposure. Each pixel can actually, each focal spot can control each pixel. This way you are able to pattern that into colorful displays. And then display can actually change color when you illuminate with different light. On the other hand, so this laser nanoprinting can also introduce what we call that energy device. For example, this one, we fabricate some perfect absorber. So as you know, the sunlight is actually a broadband. In order to achieve the conversion of sunlight into thermal energy, we need to allow the full absorption of the sunlight. This is very challenging because most of the material has a band gap. It can only allow the absorption of certain wavelength range. However, since graphene is dispersionless, that means for almost all wavelength range, it has the same absorption. So in this case, we fabricate nanostructures, grating structure using this multi-layer structure, a multi-layer graphene oxide. So in that case, the fabrication allows the slow light effect and also the grating effect helps to convert the incident light into horizontal propagation, therefore to allow the full absorption. So I'm going to talk more about this one in the later case. And then on the other hand, so we want to further reduce the thickness of graphene because graphene, it's still like nanomaterials. People may worry about the cost. Therefore, we want to reduce the thickness as much as possible and also introduce ultra high absorption. So in that case, we have like a trench structure at the bottom, which is made by copper. And then on top of that, we have a layer of graphene, which is only 30 nanometer. And then this layer, this structure basically allow the control of the response of the sunlight, and then to match the sunlight absorption. And then the absorption is actually happening at the graphene layer. So using this two design, the entire solar spectrum can be absorbed and converted into heat. On the other hand, graphene can also be made into sensors because of the electronic properties. So in that case, we made this kind of pressure sensor using this broken bridge structure. And this structure is allowed to detect pressure with very high sensitivity. So the ultimate goal for us is using a single graphene film. So we are able to pattern different devices. So for example, this one is the source communication device, RFID basically. And then the second is the energy storage device, which is a supercapacitor. And then the last one is a sensor. So if we are able to like integrate them into the same chip, that means we are able to have the communication, energy, storage, and also sensing functionality all together. So normally for the existing device is on the 20 centimeter scale, but in our case, we can make it about 2 centimeter, which can be attached to human body. So because graphene oxide is multi-layer structure, and then between each layer, there is water. So we call that water droplets. And then these water droplets is actually changing in response to the environmental change, for example, the temperature. So in that case, we actually made a temperature sensor. The temperature sensor can be really interesting because it changes color when the temperature is increasing or decreasing. So such kind of sensor can be attached to the mobile phone, for example, to kind of warn people when the temperature goes too high. So these sensors are actually quite useful because nowadays we are in the kind of international, like Internet of Things, and then big data, and then everywhere we need to have the sensors to collect the data. But we don't want to have very large sensors which consumes a lot of energy, and also in the meantime, it doesn't really look nice if you have lots of sensor kind of monitor you. But if the sensor is really tiny and then can collect multi-parameters, that is really preferred. So in the meantime, the energy consumption is also quite critical. When we have like millions of sensors, we want them to consume as smaller energy as possible. So now I will switch the gear a bit and then focus on how this Atomaterial can actually contribute to energy management or energy harvesting. So as you know that, well, on Earth, we basically get all the heating up or cooling down is all based on the sun, right? So when the sun is there, we get the energy from the sun. And then at nighttime, so this radiative cooling happens because of the outer space is absolute zero, and then therefore we are emitting the heat from the Earth to the outer space. It's very hard for us to change this because this is nature. And especially during the summertime, when it's really hot, what we can do is only use the air conditioner. However, this is not very environmental friendly. We want to, if we look into the global thermal management, like to keep us comfortable and also to for industry use as well. This cost is really, really high. It's talking about $44.75 billion in 2020. And also this leads to lots of CO2 emission. So really the dream is, so if we are able to control, if we feel cold and then there is sunlight to help us to warm up, and then if we feel very hot, and then this radiative cooling will happen. So that will be perfect because both of these way, they don't require us to consume energy. It's like natural way. So we can't do that before, but now if we look into the spectrum, we notice that the sunlight heating up the Earth in the visible to near infrared range, and also for the radiative cooling part, is actually happen between 8 to 13 micrometer. So spectrally, we can separate that very nicely. So if we are able to have something that is able to only allow the sunlight to coming in to heat up during winter time, that'd be perfect. And then in the meantime, if we are in the summer, we only have the radiative cooling without having the sun to heat up, then we don't need air conditioner. But this is challenging because we need broadband absorber, and also this bandwidth need to be very much very well controlled without really having the other impact. So how could we do this? So if we look into the thermal part, we really need to harvest the solar energy very efficiently. So if you know that silicon is basically the current solar cell that we've been working on, but the silicon is basically can only absorb the visible part up to 1.1 micrometer. That means all this near infrared wavelength range is wasted. So it won't be able to convert it into useful format. So if we are able to use solar thermal conversion, we are able to have both the visible part and near infrared part that can actually help us to achieve very high efficiency. As I mentioned just now, actually using graphene, we are able to do this because graphene has very broad absorption band. So from UV to even terahertz, it has 2.3% absorption for monolayer. So if we are able to have like multi-layer and then have this pattern, so ideally we're able to achieve really broadband absorption for the entire solar spectrum. So in this case, you see that we made the nanostructure, which is only about 90 nanometer in thickness. And such a film, if you don't really have the structure, it won't absorb the entire solar spectrum. However, by using the conversion of this metamaterial as well as the grating structure, so we are able to have this very broad absorption band and also achieve the conversion of sunlight into heat very efficiently. Within 40 seconds, you can see that the temperature increased to 160 degrees. And also, we can enlarge the fabrication to achieve quite large-scale films. So I mentioned this for the three-dimensional control. So in terms of matching the solid spectrum using the two-dimensional structure, and then with a 30 nanometer layer of graphene, this one can achieve very good absorption. So you see that this absorption is confined within the graphene layer, and the entire conversion can be very efficient. So these are the experimental result. So by using copper foil and then laser fabrication of the periodic structure, and after a coating of 30 nanometer graphene, you see that this absorption is really strong. The entire structure become dark, and then under sunlight, it can achieve 83 degrees immediately after less than 1 minute. So that means we are able to convert the sunlight very efficiently into heat. So what we can do with it? Actually, the graphene can be really nice like coating to do the water desalination, like convert seawater into drinkable water. So this is like conventionally, you basically need the reverse osmosis, which is very costly in terms of energy, in terms of the effort. But using this sunlight to heat it up, basically the sun provides all the energy, and then by heating up the seawater, you basically separate the pure water by generate the vapor from the sea. So in this case, we also developed this kind of Janus structure, which is made by just single exposure of the graphene oxide. You see that at the bottom, it still maintains the graphene oxide structure, and then on the top, it actually have this reduced graphene oxide structure. The reason we want to have this 3D and 2D structure is the 3D structure actually helps the absorption of the sunlight, and then the 2D structure allow the water to actually get through. All these gaps can help to generate the water channel, and then therefore this one is a natural separator for seawater. So using this method, we can make this kind of solar to vapor generator. So this is the graphene film, and then we have seawater injected from the needle, and then by putting that under the sun, you will see that lots of vapor generation, and the entire conversion efficiency can be very high, more than 90%. So we also measured the quality of this generated water and then compare to the WHO drinking water standard. The water is actually from St Kilda Beach, which is a beach just near Melbourne. And we found that after the desalination or processing, we can actually achieve really high quality water. And then this one is what we generated. And then this is the seawater, which is very conductive. That means got lots of ions in it. And this is in comparison with the ionized water and also domestic drinking water. Our one is actually quite pure. So we also produced a prototype, and then such a prototype can operate. So by putting the seawater into the machine, you can actually get clean water from the other side. This we can also use it like the solar thermal. We can also use that for other applications. So for example, hydrogen generation. Most of the hydrogen generation currently based on the electrolysis. So which means using electricity to split water. But this way, it costs a lot of energy to generate that electricity. So in our case, we have this photothermal generation. So basically having our graphene oxide layer, graphene layer, and we load with photocatalyst. And then this photocatalyst can actually help to split water by making use of the heat, because the heat elevates the kind of reaction or release the reaction condition. And then this way, we are able to make this chamber, design this chamber by using two different catalysts to enable the separation of the water. So such kind of device can be made modularized and then to produce the hydrogen for different applications. So we also designed, fabricate this kind of device. This is the real device we fabricated. So this module is quite tiny, but when we connect that into series connect that into large scale, you can see that this is a floating device. It can actually float on the sea surface. So I'll just show you one video. Yeah, this is basically our floating device on the water side. You see that hydrogen and oxygen are separated. So using this method, we can actually scale up the device into large scale, for example, like 100 meters or several hundred meters. And then we're also able to produce large scale graphene using this roll-to-roll fabrication method. So after talking about the photothermal, I'll now talking about the cooling part. So talking about radiative cooling is basically how can we make structures that is able to facilitate 8 to 13 micrometer that emission. So here is basically what we did. We made a multi-layer structure, and then the structure is fabricated into this periodic structure. And then this periodicity is actually matching the 8 to 13 micrometer emission. And then in the meantime, we also have a layer of reflection to avoid the sunlight. So the fabricated film is basically put into this chamber. The chamber doesn't contain any like active device. You see that this is a temperature inside the chamber. This is the temperature outside in the environment. So after the film is put into the chamber, is aluminum. Just try to avoid the conduction and convection. And you see that the temperature can immediately decrease. So this is basically providing a way to reduce the temperature without using any energy. So thinking about how to scale up, because it's a periodic structure, we actually use the laser to help us to fabricate a mold. And then after we have the mold, we can use this roll-to-roll method to make that into large scale. So in this case, you see that it's very colorful because the nanostructure is diffracting the light. And then we can make that into as long as you want. And then this one can be integrated with all sorts of applications. So when we measure when we quantify the cooling performance, you will see that in the daytime, the temperature can reduce about 8.5 degrees C, nighttime about 5.5 degrees C, and without using any electricity. And this can be used for all sorts of applications, including like cars and also buildings or food. And very recently, we also started this application in the greenhouse. The greenhouse application, you may not be able to imagine, because greenhouse normally people think that it's supposed to be high temperature, but actually plants doesn't really like high temperature. And then we want to control that temperature, but without impact the plant growth. Therefore, we need to make sure that the photosynthesis is conducted without any impact, and then in that case, we need to control the spectrum very well. So we integrate our thin film into the greenhouse. You see that these are this color, blue color is actually the one we integrated, and then the plant can actually very happily grow at the inside the greenhouse. And then we measured the energy consumption. We found it's about 20% reduction of the cooling cost, and also 20% reduction of the water usage. So that means the cooling film can make a huge difference in the greenhouse. We also made a large-scale film and then integrate that into we also made our own greenhouse. So this one, we actually made that into, we call that industry trial. So the previous one, this one, was in a state-of-the-art research-based. And the current one, this one I show is actually for the industry trial in Victoria. So all these greenhouses are going to be integrated with this cooling film. And we actually found the plant yield has also been kind of changed. Most of them are actually positive change. This is also very good news for us. So really talking about the how this atomaterial and light can actually change the food production. So thinking about the greenhouse now, which requires lots of solar panel to power to provide the electricity. But actually in future, by using this kind of natural cooling or natural heating or renewable energy, what we would like to achieve is really this kind of greenhouse anywhere, even in the urban area, that can self-sustain, that can produce lots of healthy food, and which is readily available to everyone. And then in this greenhouse, there will be like monitor using the sensors and using big data. So this, I believe, is not going to be quite far away. So the last part, I still have a few minutes. I'll just quickly talking about the integrated devices. Because this atomaterial also have really, really nice nonlinear property, because we know that when we talk about integrated devices, if you really want to achieve large signal to noise ratio, like high speed, you will need to make use of nonlinear property. So for graphene oxide, it really has large second order and third order nonlinear property. That means it is able to enable many phenomena. So for example, all optical wavelengths conversion, all optical switching, and also mode lock lacing, and also this quantum optics. So in our case, we also quantified the nonlinear property of the like graphene oxide layer. So we want to know that for monolayer, what will be the nonlinearity, whether there is any nonlinearity. We measure the layer dependence for single layer, 3-layer, 5-layer. Actually, you can control the layer number very precisely. We found that graphene oxide nonlinearity is really amazing, because you see that this is nonlinear absorption, this is nonlinear refractive index. It's actually quite high even for a monolayer. And then after measuring this one, we quantify the nonlinear property. You see that this is basically the linear absorption, and then this is the nonlinear refractive index. And we found that because we want to achieve that low linear absorption to reduce loss, in the meantime, we want to have high nonlinearity, therefore enable all these like all optical devices. We found that compared to other materials, graphene oxide really gave you a good property. So in terms of in terms of linear absorption, it's really low. So which is orders of magnitude lower than other 2D materials. And in terms of N2, is actually orders of magnitude higher than other Atomaterials. So that means this is really good news for integrated devices. So we integrate graphene oxide with different materials, including silicon, silicon nitride, Hydex, and silicon oxide. We found that the integration is really quite handy because of this self-assembly method. And we found that the coupling is also very efficient. And after the integration of this graphene oxide, the nonlinear property of these devices, all this integration have improved. So I won't go into too much details, but if you're interested, you can have a look at the device performance increase. So for all of the devices, after integrating one layer or two layer of graphene oxide, you can see that the nonlinear conversion efficiency increased dramatically. Some of them even more than like several tens of dB increase. So that means even with the existing architecture of the device, by only applying one or two layers of graphene oxide, you are able to dramatically improve the device performance. So this is really good news for the current communication system because you don't need to change dramatically the device configuration. So due to the time limit, I won't be able to go through all this integrated device, but if you are interested, you can take a look at a few review article we wrote recently, talking about Atomaterials, talking about integration. And this will bring to the conclusion of my talk. So basically, by using Atomaterial, you're able to introduce many different properties and also enhance performance of the existing device. So to make the current device much smaller and then energy consumption much less, and also the speed can increase a lot. So this integration can be in a communication device, can be in biomedical device. It can be also in some other device like VR, AR, meta device. So therefore, I think if we are able to put more effort into understanding these Atomaterials, we should be able to develop devices with better performance. So in the end, I'll just use 1 minute to just introduce one journal to the audience. So we actually have a new journal called NPJ Nanophotonics, which is focusing on nanophotonics innovations. And also this one is open access for not only the traditional academics, but also industry. We would like to publish industry findings as well. So we have lots of familiar faces. Probably here you can see that our editorial board members are really like leading researchers in the nanophotonics field, and hopefully you can support our journal. So in the end, thank you so much for your attention.
Thank you very much, Baohua, for a wonderful talk. It's exciting to see the real application of, nanophotonics. Now we were going to go into the panel discussion. So what I'll do is to, let's see. Okay. Why I can't find my file to show, okay, here. So, okay. So let me now introduce our panelists tonight. Our first panelist is Professor Fan Wang, who is from the School of Physics at Beihang University. His research interested on biophotonics, nanophotonics, super resolution microscopy, and optical tweezers. Professor Fan Wang has published 80 peer-reviewed journal articles, including 13 Nature series journal, as well as many papers in Nature, Nanotechnology, Nature Communication, and Life Science and Application, etc. He served as a young committee member of the Biophotonics Committee of the Chinese Optical Society, and also as an associate editor for Frontiers in Chemistry. Professor Fan Wang has won several awards, including the Australian DECRA Fellow Award, the Davis Time Research Prize, and the iCANX Young Scientist Award. Our next panelist is Professor Lin Han, who is working in the Department of Precision Instruments at Tsinghua University. He obtained both his bachelor and PhD at Tsinghua University. And before joining Tsinghua as faculty member, Professor Lin worked as a postdoctoral associate at University of Michigan, Dearborn, and the University of Texas at Austin. His research involves nanophotonics, laser nanofabrication, multi-scale laser modification technologies. He has published over 60 peer-reviewed papers in the journal like Science, Nature, Photonics, Science Advanced, and etc. His research was highlighted in many media, such as Nature Science, Nature Photonics Materials, and the Discovery Channel, so on. Professor Lin has also served as associate editor of Photonics and the young editorial board member of Ultrafast Science Exploration, Nanotechnology, and Precision Engineering. Our next panelist is Professor Guangming Tao, who is a professor at the Wuhan National Laboratory of Optoelectronics and the School of Material Science Engineering, Huazhou University of Science and Technology. Professor Tao is also the director of Intelligent Fiber and Sports Health Technology Institute, Wuhan Institute of Industry Innovation Department. His research interests include interdisciplinary research on passive thermal management materials, intelligent fiber and fabric space, and minimally invasive medical fiberbot. He has published over 100 papers in journals, including Science, Robotics, and he also holds 50 patents, and with 23 licensed and transferred. Professor Tao's research group received many awards and also being widely reported in different media. And he's also currently the deputy director of the Division of the Fiber Materials and the Composite Technology of China Materials Research Society, and also associate editor of Advanced Fiber Materials and many other journals. So without further ado, let me just invite all our panelists to the stage. All right, so now our panelists, please feel free to ask your question. Who would like to start first?
I probably ask the first one. It's really fancy and a really nice talk. Thanks for the talk. So
Thank you.
I want to firstly ask one really easy question about the flat lens, because I'm quite interested in that one. It's got a really good focus, I see. So because I saw your design, just you basically just change the amplitude, make it like a transparent or not transparent, right? For the first version one, right? Only change the amplitude, right?
Almost all of
So
them change amplitude and phase simultaneously.
simultaneously, okay.
Yeah, simultaneously. Sorry, if you remove the material entirely, then you only change the amplitude. But in that case, we actually have reduced graphene oxide and graphene oxide. So that's the contrast. It's not between graphene oxide and air. So that means you have both amplitude and phase change.
Okay. So the question I want to ask is because I saw you make it like a thinner lens, or it's more like a zoom plate. And so zoom plate is like you just change the half wave number. So for the zoom plate, you already have multiple focus. I saw in your the next generation paper you did like make it multiple focus, but for the original one, can you solve if you only want one focus, how can you solve this problem?
Yeah, actually, just as I mentioned, you can change both the phase and amplitude simultaneously. Therefore, you are able to design all sorts of phase function into the lens, and you can actually add them together. So there is no need, like it's not like exclusive, like you can only have one function. So therefore, in the first lens, we actually try to achieve the best efficiency. Then we try to achieve like single focus rather than like multiple focus, like reduce the other orders of diffraction. But in the later cases, so you can actually design different phases, different phase function to allow you to either have single focus or multiple focus. So later on, I think we can achieve 4 focal spot and also several orders. Yeah, so this for the OAM beam also the same. We can achieve like different OAM beam at different order.
Okay, super nice. Lan, can I ask another question, or we only? Okay. Yeah, probably ask another one. Yeah. So I'm also quite interested in you talk about the high nonlinearity of the graphene oxide. So because usually we need to use the lithium nebulate the crystal, so that is the conventional one. But for the fabrication of that one, it's really painful. But if your graphene can achieve the same order, like a kind of the Chi3 or some parameter, it's gonna be really beautiful, and because easy to fabricate. Can you conclude this kind of direction, the application side? Yeah.
Yeah,
Compare with
very interesting question. Due to time limit, I couldn't really talk too much about the integrated photonics, that part. But we did find that for graphene oxide in particular, and reduced graphene oxide as well, the nonlinear property is very rich. So first of all, the nonlinearity is very high. So talking about N2 over beta, so that means the nonlinear figure of merit, which is the parameter we want it to be as high as possible. This is higher than silicon on insulator. So that means it's probably one of the highest among all the materials we know. And we tried the integration on different platforms. So the integration result is actually quite promising. I think the only problem with the current material is the absorption. So if we are able to further reduce the absorption, then I feel that the application could be very broad. So it can be used for like supercontinuum generation, like nonlinear switch, and also nonlinear wavelength conversion. So this part, there are still lots of possibility to try. That's why I think this is the purpose of this talk. Then everyone can actually use this method to try different the device configuration.
Okay, really nice.
Yeah, thank you.
Hi, Professor Jiang. Hi, this is Gongmin.
Hi, Gongmin.
It's very interesting to see now you have a much bigger greenhouse. So from my side, the cooling film is a kind of optical modulator. So so here's the question. So what type of light? I mean, how to modify the solar spectrum to make the vegetables or the plants to grow better or happier?
Yeah, very good question. I actually enjoy that very much. So each time we go to the greenhouse, we get free vegetables. I can actually test whether it's sweet or not, or the taste whether it's good or not. I think in terms of the greenhouse, the key parameter is not only on the energy part. So energy is very important because energy cost determines whether greenhouse can be deployed into a large scale. But in the meantime, you also need to consider whether the plants can the plants yield and nutrition, and also the kind of so how many runs you can produce. So all these parameters you need to consider. So in our case, we actually grow in different conditions. So for example, in Melbourne, in Queensland, so at different condition, we tried the cooling film, because the cooling film will function differently at different weather conditions. We found that normally for plants, they need red and blue for photosynthesis. But in order to generate better result, you really need to understand that plant well. Each plant has, or each species has different kind of reaction or need. So for example, the leafy one and the fruity one, they have entirely different need. We found that the use of the cooling film, that can actually make the plant absorb water more efficiently. Because the temperature is cooler, and the leafy plant, they grow much, much better. And also for fruity one, we need to make sure that the UV part is actually passing through a little bit. And this one we can do because we have our nanostructure and also coating. The coating will give us different spectrum response as well. So it's basically a combination of this one we started from 2016. So now it's already like 8 years. So you need to grow many, many rounds and then understand the reaction from different species. And then you can have like a data matrix build up, and then you see that which season and which city I need to have what kind of film. But it's very interesting. I enjoy that.
Yeah, thank you. So I think there must be some nanostructure or microstructures on the surface of the film. So would that be easier to clean the film?
Yeah, very good question. Very good question. We actually have our protection layer. If you have so there are two ways to do this. The first one is we made that hydrophobic. So hydrophobic, that means you don't have lots of like water or residues. The second one is we have a layer of coating to protect that nanostructure. Otherwise, there will be like easily get dirty or get damaged. Yeah.
Thank you. Thank you.
Yeah, very important question, because otherwise in the application you will have lots of problems.
Yeah. Thank you.
Yeah, thank you.
Hi, Professor Jia. This is Lin
Hi,
Han.
Lin Han.
Thank you very much for the wonderful and very inspiring talk. I
Thank you.
think graphene is very fantastic material, and it brings us a lot of new physics. And I think in your work, you're trying to incorporate these kinds of material into some photonic devices or some optoelectronic devices. So you're trying to change the world using this material. So it's very
Thank
nice
you.
and very impressive. I have a couple of questions. So basically on some technical details. The first one is on the set assembly of graphene oxides. I remember you just mentioned that when you do the set assembly, you need to control the surface charge of the substrates to make it positive. So I'm just curious. So what's the forces between the graphene oxide flake before the set assembly and after the set assembly?
Oh, very good question. Thank you. I think depends on your application. So for example, the flake size, eventually they need to kind of stitch together. If you have too large and then or too small, basically you need to have lots of them stitched together. So we found that for optical application, we actually need a bit smaller, because we want the like the how should I say, optical absorption. You want to have less absorption, like less loss. Therefore, you want them to really stitch very kind of tightly. But for electronic property, because large flakes actually gave you large continuity.
Yes.
So after you reduce, you have that basal plane in a larger scale. Therefore, the conductivity will be better.
Yeah.
So these are quite dependent on your application. But we found that normally it's on the order of 1 micrometer. So the flake size, smaller or larger, that's the kind of middle line.
Okay, I see. So we know the graphene oxides flake are dispersed in some solvent like water, right? So do you need to introduce some repulsive force to make sure the flake will not stick to each other?
Yeah, very interesting question. Originally, we thought the same. And then later on, we found that it's actually no need, because after the synthesis, they all have negative charge.
I see.
They have repulsion naturally.
Yeah,
Yeah.
I
So
see.
and also the only thing is you need to make sure you have monolayer. Because if you don't have monolayer, and then you cannot really control your layer number. But if you have monolayer flakes, and then your self-assembly is going to be monolayer in a large scale, because the second layer will be repelled, right?
Yeah.
So it won't be attached to the first layer.
I see. Thank you.
Yeah.
And my second question is on the laser reduced graphene oxide. So basically, you shine the laser on the graphene oxide to reduce the material. But as far as I know, laser can also oxidize graphene. So when you shine a focal laser on graphene, you can cause something like sublimations or oxidation. And sometimes you can get some, carbon oxide or carbon dioxide, which is gas-based. And on the solid state graphene, sometimes we can also get some graphene oxide. So it seems to me there's a trade-off between the two processes. So is there any trick to control the balance between the two processes?
Well, actually, because today the audience is very broad, I didn't really go too much into the depths. I mainly talk about the application side. Talking about reduction of graphene oxide, there are lots of research on that aspect. It's actually, I would say, we even till today, we still don't know the entire picture. What I can say is, laser can do a lot of things. If you control the laser power or laser energy well, you are able to chop off the oxygen-containing group. But if you provide additional environment, so for example, like you mentioned, CO or CO2, this kind of environment, by further increase the laser energy, you're able to initiate other chemical reaction. So for example, like further oxidation. But we need to control that kind of reaction condition very well to just make sure that it's being chopped off without really coming back. So in this case, we most of our reduction were using femtosecond laser. Femtosecond laser, you probably know that it's a like cool fabrication process compared to other continuous laser or nanosecond. So in this case, the heat accumulation is much less. But we also noticed that using femtosecond laser, so if you change your pulse oscillation or pulse shape, so you are able to control the chemical bond to some extent. So this is called laser-induced chemical reaction. on that aspect, I think it's just the start of understanding this process. There's still like long way to go. So
Yes.
I think you raised a very good question.
Thank you.
Yeah,
I
thank
still
you.
have very quick question with the last one. So after the laser printing, is it possible to to reduce the graphene oxide between the reduced graphene? Is it possible to remove it?
You mean entirely remove from the substrate?
Yeah, because we just reduce the graphene oxide selectively. So
Yeah.
between the reduced graphene, there's still some graphene oxide, right? So can we
Yes.
remove these kinds of graphene oxide?
I think you can, because I'm not too sure what's the purpose of like remove the graphene oxide, but what we did before was if you increase your laser power continuously, you are able to remove the reduced graphene oxide. But the other way around, so if you like change your focus area and then increase the power and then remove the graphene oxide, I think it's also possible.
Yeah.
We found that actually the remove process is also very interesting. If you can control the laser parameter very precisely, you are able to actually peel off the layer, like layer by layer. So
Yeah.
that's where we made that display, because the film thickness or layer number will change the interference
Exactly.
condition, and then eventually you will change the color. So I definitely believe it can be done, but you do need to have a very fine control of your fabrication condition.
I see. Thank you.
Yeah. Thank you.
Oh, well, okay. I think I am on. Okay. I just have a very general question, Baohua, about you've shown that real exciting application agriculture by using your nanostructured film. So what is the sort of the cost to make those kind of film in compared to other competitive technology? Because there are also other material using based on similar sort of principle.
Well, you always ask the best question, right? The
Oh,
$1
it's just a
million
very
question. Yeah. So actually, the cost compared to other, I think Gongming in this case should have much better idea, because there are other materials like naturally available material also have this cooling effect. So they can be really cheap. So in our case, our structure is a little bit more expensive than the others, like naturally available ones. We're trying to reduce the cost by using the roll-to-roll fabrication method. But the other thing is we need to really think about performance. Because in some cases, you need that high performance to reduce the temperature. If you think about the naturally available material, they basically based on the material intrinsic property to reduce the temperature to have the radiative cooling. But in our case, we basically make use of the intrinsic plus the nanostructure. So therefore, the performance should be better. We can have precise control of the spectrum range to cover that like almost square kind of spectrum. Therefore, the performance can be much better. Well, I think the cost is really related to the scale, right? So when you scale up, the cost will definitely coming down, in particular for this roll-to-roll printing method. That's why we aim to have some very like high-end applications, and then sometimes the naturally available material may not be able to do. And also we make our film flexible. So flexibility is also another very attractive factor to talk about the application. I think eventually we aim to make that comparable to the naturally available material and still maintain that high performance.
Sure, I can understand that. But for agriculture, when you talk about fruit and the leaf, plants, vegetable, What is the measure of a success? Basically, it's like it tastes nicer or some. How can you actually really say that's, I'm really tailored the spectrum and I grow the best fruit or something?
Yeah.
Because how you evaluate that?
Very good question. So I think really depends on the perspective from who we talk about this. So if we from the perspective of grower, they want better cost effectiveness. So after applying the film, whether they can reduce their energy cost, whether they can have more fruit production. So from this point of view, we actually have this return on investment calculation already done for our film. We found that around around 2 years, depends on where you apply this material. So for example, in the very hot area like Darwin or Gold Coast, this kind of area. So it's very quick, like return on investment. In Melbourne, probably not too good. Yeah. So that's from the grower's perspective. And then from the customer's perspective, really the nutrition and also the kind of color sometimes, and also the size of the fruit. We found that by using the cooling film, actually the growth is being changed because the spectrum being changed. And also the water condition, the humidity inside the greenhouse. So in that case, we found that for lots of plants, they actually become like nutrition-wise, like increase, and also the size of the fruit increase. So that's all good news. But we do find for some like the plant requires a lot of sunshine, so a lot of high temperature. Maybe like so in the like very high temperature one, like mango or something, that might not really be the best option. But for most of the fruit and the vegetables, they actually increase the production. Yeah. So I think overall it's really depends on where which perspective we see this point.
Well, wonderful. That's really interesting to know. I guess we do have a time for last question. I would like to take this opportunity to ask you actually, because I think that's very relevant to a lot of people, maybe our audience, young researchers who really want to translate their technology. I would just like to ask you, I can see you're very successful and to build this translate your nanophotonics, innovation into a real application. What is the most challenging experience to you as a, do a scientist now and do a lot of application? Can you just share a bit of your experience?
Oh, thank you very much for asking this question. I don't know whether it's successful or not, but I can share our like unsuccessful experience. Actually, I started to do this like application relevant research since 2008. I actually very passionate on like solving real life problems because I found that doing science, if you only enjoy by yourself, then that's a little bit selfish, right? So you need to have your like fruit or research result to be tasted or to be felt by all the people because they actually pay your research. So I found in the translation aspect, one of the first challenge I met was, well, we are the technology developer. We always thought, our technology is the best. But actually, when you really stand from the point of your customer or of your user, you have found that there are lots of problems. But when we first start with not understanding their problem. So I think that's actually after that change of the mindset, I can actually hear their problem from the very beginning when I developed the technology, and then really work with the team to try to change their mindset as well. This is, I feel, is quite critical. Otherwise, the technology may look so fantastic, but it doesn't really do anything to the end user.
That's right. That's wonderful. Yeah, that's exactly. I think I can see you becomes also expert in agriculture and all this, right? So you learn a lot.
Far away.
Yeah. All right. I think that's what we have all we have the time for tonight. And so let me thank you, Baohua, for a wonderful talk, and also thank you our panelists for very great discussion. So let me again share my screen. Okay, that's the one. Okay, so here is the certificate that Alice will send to you later this night, I think, to recognize your great contribution to the iCANX talks. Thank you very much for joining us tonight. So this is a reminder that our first iCANX Davos Summit will happen in July 11th to 12th. So you still have time. Please come and join us. It's going to be fun. And next week, we'll have our speaker is Sam Zhang from Harbin Institute of Technology. He will talk about the progress in infrared transparencies under electrothermal and mechanical environment. So please come join us. With that, thank you very much, everyone. Thanks for joining us, and hope to see you next time.
Ladies and gentlemen, my dear friends, welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics: innovation, science, technology, investment, management, and entrepreneurship. Short for It's Time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have a Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future. We also invited all these world leaders, scientists, investment management to go together to talk about, what technology and science going to be for the future. And we're going to listen to many sharp talks. All these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invited you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions, parallel sessions. You are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us. And it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
在持续发展的社会中，电子元器件需要应对日益复杂化的要求和越来越高的期待。技术革新浪潮汹涌而至，对其高性能的需求、无限小型化的追求， 成为行业发展的必然趋势。多层陶瓷电容器、电感器、高可靠性元器件、太阳诱电支撑起全流程的先进技术，提供给用户全方位的服务。为了科技的发展，我们一代代太阳诱电人肩负使命，激情拼搏，以极致的匠心独运，呈现出史诗级作品。研发历程感动了无数电子工程师。太阳诱电将深深吸引全世界的目光。
先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 iCANX 达沃斯科学峰会。那今年是第一次 iCANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有6个主要的议题。第一个是创新 innovation， 第2个是科学 science， 第3个是 technology 我们的技术，第4个是 investment 投资，第5个是 management 管理。